Welcome to Chapter 7. Now we get into 3D, and this is lecture number 26. And the main thing to remember here is that, something we talked about earlier, is that when you have a unit vector, any unit vector, and you want to take the time derivative of that, you need to look at how that unit vector is rotating, and we need to cross it with that unit vector. And I just stuck in the E here, but it could be I or J or K or anything. And the big difference from chapter 6 is that now omega is a vector, and maybe it's going to have different components. In a planar problem, remember, omega was always in the K direction, right? Like it was always like out of the paper. Let's see if we can get that focus back. It was always out of the paper, but now omega could have some other components. And I think that will make more sense when we do an example. So here we have an example motor problem here, where we have some motor and there's a couple things going on where like this base is maybe rotating, except that was in a different problem. So here n is 0, and then there can be some rotation about this axis, and that's the kind we're talking about here. And then also this part is rotating with some omega naught. All right, and so for this particular problem, they're going to tell us that n is equal to 0 and that this gamma variable is changing. And specifically, if they say that gamma is going to be increasing at 3 pi radians per second. So if we wrap that around, an increasing gamma is like in the positive, it would be like a negative number if we were going to assign it about the x-axis, right? Because when we increase this and we curl our fingers, right, it would be going around the opposite way as this arrow. So if you draw it in this arrow in the positive x, it's going to be a negative sign. Okay, so that's all the things that are moving in this, and they give us this omega term. And what they want to know is what is first they ask for the angular acceleration of the rotor. And now that might seem obvious, like, omega naught is constant, and this gamma dot is constant, so there's no angular acceleration, everything is constant. But it's not true, because what's happening is that the direction of this angular velocity is changing because it's rotating about this axis. So it will because of the direction. So let's think about this a little bit more rigorously. So we're going to have our alpha is going to be the change in our omega. But now, like I said, omega and also alpha are both going to be vectors. So if we take the derivative of the angular velocity here, so we can start by having some angular velocity, and we're taking this derivative. What is going to change? It's not going to be the magnitude, but the direction will be changing. I feel like camera focus issue. Okay, so this is the thing that's going to be changing. So we need to find this derivative of k hat. And so k is in the z direction. All right, and it rotates, and typically we think about it, the coordinate system rotating with some big omega. And so we're going to have some k hat dot equals big omega cross k hat. And now this big omega is going to be in the negative I direction, like we talked about here before. And where I is fixed, so that is not changing. And in fact, we could have added to this omega term, we could have added even a component in that I direction, but this axis isn't rotating because this n is 0. All right, so we've thought about everything that's going to be rotating. We think about our change in angular acceleration, and so that means we can bring down, we've got this negative 3 pi here, and we have our I cross k. But actually, this is going to give us a negative, so that the negatives cancel out, and we can just multiply this out and get our answer for our angular acceleration. It's going to be in the j direction. And now let's think about, does that make sense with our problem? Yes, so there would be some angular velocity vector that would be here, right, if we curl our fingers, and then it's moving because this is increasing, so it's going to be moving to some new vector here in some small short time step that's going to be related to this, and it's going to be in this direction, which is in fact the positive j direction. So that should make good sense that it's in the positive j direction. All right, so now they also ask us to find the velocity and acceleration, and this is also going to take us a minute to kind of think about this pretty carefully. But we know they give us this OC distance and the CA distance, but what we really want to think about is the OC vector plus the CA vector. So that's going to be 10 inches in the K direction, if we think about this as K, and then 5 inches in some R direction, and I've sort of drawn a unit vector here. And the reason I didn't just call that the Y direction is because I want to let the unit vector R be rotating with the disk. So it's going to rotate with whatever gamma dot is, but also with omega. All right, so now if we take derivatives of this, we're going to have that 10 inches, but we're going to think about, so this K is rotating with the I. So just like we talked about K dot here, we're going to calculate the same thing here. And now this 5, this R is going to be rotating in the I, but it's also rotating in the K direction. And at this instant, that R is in the J direction. So for this instant, when all these things line up, we can take cross products and get some velocity here. And again, like we want I cross J, that's going to, I cross K, it's going to be negative J, but there's negative sign, so it cancels out. I cross J is going to be positive K, and so we keep the negative sign, and then K cross J is going to be negative I, so we introduce a negative sign. And that agrees with the answers that the book has, although they're like weirdly pulled out the 5 pi for some reason. Okay, and now let's go to acceleration. Now this is where people mess up, because you have to remember, like if you're going to start with this equation here that we derived here for the velocity, and we're going to take derivatives of that, we have to remember like which of these are rotating in which ways. So that first one, that J, that is actually from a coordinate system that is rotating at negative 3 pi I. But these unit vectors are rotating at negative 3 pi I plus something else in the K, this 122 pi over 60 in the K, because I'm just converting from revolutions per minute to radians per second, which we always want radians per second. So, all right, so if we calculate that out, just taking those cross products of those vectors, again, we can get what they have in the book. So in robotics, we have this problem obviously a lot. There's one rotating thing attached to another rotating thing attached to another rotating thing. So the way we do this is we have coordinate systems. And so let me show you a quick example of how this will work. So here's a robot with 5 degrees of rotational freedom. And the x and y axes are attached to the base ring, which rotates at some rate. Let me show you the picture. So here we have all these different axes. So and they're always numbered in the same way for a robot. We always start the numbering for at the base, and we move toward the end effector. So this will be the first one and omega 1, which then rotates whatever omega 2 is, some omega 2 joint, which then rotates omega 3, omega 4, omega 5. And so normally we would have a different coordinate system kind of for each joint, but here they're trying to make it easier for you, and they only have 2 coordinate systems, and then they kind of work with it in there, but either way. So there's going to be a coordinate system at joint 1 and some coordinate system up here, which is actually at joint 3, since they're kind of doubling up, I'll show. And the important thing is that at some instant that we care about, the x1 is the same as x2, but they might have different rotational speeds, different angular velocities. But at some instant here, they're all lined up, which will make the math a little simpler for you. All right, so let's think this through. First of all, that first coordinate system, omega 1, that's going to be here. It's kind of centered here. There's an O1. That's why I kind of decided to do it this way. I think that's what they're trying to get us to do. How is this rotating relative to some fixed space? Well, it's rotating with some omega 1 about the z-axis. And you can see it's about the positive z-axis if you use the right-hand rule. So we're going to have some omega 1 equals omega 1 in the k-hat direction. And now omega 2, so how is this set of axes rotating? Well, we're going to have, it's going to be rotating at omega 1, so we'll repeat that. And then we're also going to have some omega 2 in the I1 direction, because now this vector x, like when this changes, this will be something different. So that's why it's important to keep track of the subscripts. All right, and then we're going to have, there's also some rotation omega 3. And omega 3 is going to depend on theta, which comes from the rotation of omega 2. So actually, omega 2 is theta dot. And now we can express how the axis that omega 3 rotates about in that first coordinate frame. Some cosine theta I hat sub 1 plus sine theta j hat sub 1. And I feel like this is kind of hard to read. Try to like make this nice and dark, but so that's a j. All right, and now so for the jaw then, it's going to be rotating, this little jaw piece here is going to be rotating whatever that first coordinate system is rotating, plus also now omega 4 in the I2, so here's I2, and then omega 5 at some other axis here, and we can find what this axis is here with the cosine of theta minus beta if we wanted to have everything lined up. And then we would of course be adding the omega 1. So now we would have some expression for the angular velocity of the jaw in terms of all 5 of those components. But now, of course, it's a little disappointing when we get in here. Oh, and also where, of course, omega 4 is equal to theta dot. When we put in all the numbers, actually, we can see that a lot of these zero out. So like all of these numbers over here, they're going to zero out. It's just the first 2 rotations, just this one and this one that are non-zero. So the rotation of the jaw is just going to be that omega 1 in the k direction, and they tell us omega 1 is 2 radians per second, and then it's going to be omega 2 in the I1 direction, and then nothing else. So if they ask for a vector, then that's what it would be. But they actually ask for the magnitude, so fortunately these are perpendicular at this instant, k and I1, so k is because they're aligned at that instant. And so then when we take the magnitude, we're just going to take the sum of the components squared. Now, what else do they ask us for? The angular acceleration. So now we have to think about how these things are changing. And I guess I'm going to assume that all of these are constant rates because that's kind of the theme of this. But now we're looking at how they're changing. So because of rotation. So if we take this vector, now that we put our numbers into it, we've got the 2 in the k hat direction, but the k hat, there is no k hat dot because k is not rotating. So this is the base frame. This axis here, no matter how this rotates, is not going to change. So this term is going to be 0. And then this term here is going to be, this is in the first reference frame, so that we know that the first reference frame is rotating at omega 1 in the k direction from the very first thing we wrote down up here. So since we know that that's rotating at omega 1 in the k direction, all we have to do is take the cross product, and we get alpha, the vector, equals 1.5, which is from here, times the rate of change of that vector I in the first coordinate frame, 1. And that we know that it's rotating at 2k, so we just take the cross product of 2k cross with I, and we know that that equals 3j at this instant. Now, in a minute, like after this has been undergoing some other changes, we might find that now it would be in some other direction, right? Because like this would be swinging out, and so like this j would be different. But if we let it rotate, and let our definition of j rotate, then this is perfectly good. All right, and so there'll be a bunch of examples like this with lots of practice cross products, thinking kind of 3D thoughts for these problems. So feel free, if you have a specific question about a homework problem, we can discuss it at Canvas. You can ask me questions and I can post follow-ups. Let me know how it goes.